Good day everyone. Today I am using all about blood spatter, blood pattern analysis. First material is our tabs, our ruler, steel tape, our push pin, scissor, cutter, our glass, our protractor, our sponge, masking tape, our gloves, magnifying glass, paintbrush, our syringe, dropper, evidence number, our fake blood, distilled water, and our evidence bag.
And here's the ingredients we use to make a fake blood. First is distilled water, Joe Boost, Nescafe, ketchup, and cornstarch. After mixing the ingredients, this is the outcome.
First, we perform single drops. Hold the dropper at fixed height about 3 feet above the surface and release 1 drop of blood. Now, let's measure the blood stain using a ruler and evidence number. For the single drop, the width is 1 centimeter and the length is 1.5 centimeters. Next, for the drop series, move the dropper at a steady pace while releasing drops across the surface. And now, let's proceed to void pattern, and we will using a phone case. First, place the surface at a slight incline using a phone case. Next, pour a larger amount of simulated blood at the top of the surface. The length is 1 foot. Let's proceed to the flow pattern. The target surface here is smooth and non-porous, which is why the flow patterns are distinct and straight. First, we prepare a non-porous surface such as glass, which is smooth and does not absorb liquid. Next, we place it at a slight incline to let gravity act on the liquid. Then, we pour a small amount of simulated blood on the surface. As it lands, it does not get absorbed and instead flows freely across the glass. The pattern appears clear and well defined as gravity pulls it downward, forming a continuous trail. We measure the length of the flow pattern using a ruler to analyze how far the liquid traveled on the smooth surface. The length is 5.3 centimeters. First, we prepare a porous surface such as fabric. This type of surface has tiny openings that allow liquid to be absorbed. Next, we place the surface at a slight incline to allow gravity to act on the liquid. Then, we carefully pour a small amount of simulated blood on the top of the surface. As the liquid spreads, we observe how the porous material absorbs it, causing the edges to become less defined compared to a smooth surface. The flow pattern appears wider and more irregular because the liquid is drawn into the tiny pores of the material. The length is 3.9 centimeters. Finally, we measure the length of the stain to analyze how far the liquid has traveled and how much it has been absorbed.
Next is projected blood stain patterns. These patterns are formed when a force greater than gravity acts on a blood, helping investigator determine the direction, force, and possible cause of an accident. First, we simulate blunt force trauma. We saturate a sponge with blood and place it on a hard surface. Then we strike it firmly with a wooden block. We observe how the droplets spread out of radial patterns. Next is low velocity impact spatter. Low velocity impact spatter appears as large circular stains typically over 4 mm in diameter. It forms when force is applied slowly, causing blood to fall or flow rather than explode outward. The pattern is concentrated near the source, often showing pooling in minimal satellite spatter, indicating gravity's effects. Then we proceed in cast-off pattern. The pattern forms a distinct curve or a linear trail of droplets, varying in size and spacing. It shows blood flung outward from a moving object, creating a line that indicates direction in motion. The stains are elongated and their distribution reveals the arc or swing path used, typically of repeating striking actions. Next is arterial. Finally, we simulate arterial, spurting, and expiratory system. For arterial, we use a syringe to project blood in a compulsating manner, creating a wave-like pattern. For expiratory, we use a spray bottle to create a mist of droplets. We observe the differences in droplet size and density between these two. Next is contact patterns. First, we create a contact patterns. We apply a thin layer of simulated blood to the bottom of a shoe or a glove's hand. Then, we press it firmly and straight down onto the paper without sliding. When we lift it up, we observe if the details like thread, patterns, or ridges are clearly visible. Next is wipe patterns. Then we have wipe patterns which show movement through existing stains. We place a drop or pool of blood on the paper and wait about 30 to 60 seconds for the edge to start drying. Using a clean object like a paper towel, we drag it directly through the center of the stain. We look for the skeletonized ring that remains, showing where the blood had already started to dry before it was wiped. Next, we create swipe patterns, which show the motion of a bloody object moving across a surface. We apply blood to a glove hand or sponge, then place it on the paper and drag it across in a single smooth motion. We observe the pattern, identifying the start point where the blood deposit is heavy, and the feathered end point where it tapers off as the object moves away. Now, we explore the physical structure of bloodstains and how different surfaces affect them. First, we look at the anatomy of a single blood drop. We use a pitette to drop blood onto paper from a height of about 3 feet at a 90-degree angle. Once dry, we examine it under the magnification to identify its parts. Pattern stain. This is the main central body of the stain. Spines. These are the pointed edge that radiate outward from the center. Satellite. These are small separate droplets that broke away from the main stain upon impact. Activity 3. Smooth surface. The stain is circular with clean distinct edges and clear spines. The diameter is well defined and the satellite spatters are clearly visible around the main stain due to the hard surface. And now, let's measure the length and the width of the stain on the smooth surface using a ruler. The length is 4.3 and the width is 3.2. Next is rough surface. The edges are irregular, jagged and broken, following the bumps and grooves. The stain appears uneven and satellite spatters are few or absent because the texture catches the blood. And now, let's measure the length and the width of the rough surface. The length is 4.9 and the width is 4.9. Absorbent surface. The stain spreads out widely, making the diameter larger. The edge look fuzzy, frittered, or diffuse as the liquid soak in, and no satellite spattered are formed. And now, let's measure the length and width of the staining absorbent surface. The length is 4.8 and the width is 5.7. Then we proceed in height increments. We drop the blood from our different measured heights. This is 1 foot, the first drop, and the second drop, the third drop. To get the accurate results, we drop the blood 3 times at each height. Then we calculate the average diameter. In the first drop at 1 foot, we see the parent stain with a length of 1.7 cm and width of 1.8 cm. In the second drop at 1 foot, we see the parent stain in a length of 1.6 cm and width of 1.7 cm. In the third drop at 1 foot, we see the parent stain with a length of 1.7 cm and width of 1.7 cm. Then we proceed in 2 feet. First drop, the second drop, and the third drop. The first drop at 2 feet, we see the parent stain with a length of 2 cm and width of 2 cm. In the second drop at 2 feet, we see the parent stain with a length of 1 cm and width of 1 cm. In the third drop at 2 feet, we see the parent stain with a length of 1.7 cm and width of 1.6 cm. Then we proceed in 3 feet. The first drop, the second drop, and third drop. In the first drop at 3 feet, we see the parent stain with a length of 1.8 cm and a width of 1.9 cm. In the second drop at 3 feet, we see the parent stain with a length of 1.8 cm and width of 1.9 cm. In the third drop of 3 feet, we see the parent stain with a length of 1.7 cm and a width of 1.7 cm. After that, we proceed in 4 feet. The first drop, the second drop, and the third drop. In the first drop at 4 feet, we see the parent stain with a length of 1.6 cm and width of 1.8 cm. In the second drop at 4 feet, we see the parent stain in spines with a length of 1.6 cm and width of 1.6 cm. In the third drop at 4 feet, we see the parent stain with a length of 1.7 cm and width of 1.8 cm. Now we will learn how to shape a bloodstain change based on an angle at which it hits the surface and how we can calculate that angle. We place our paper on an adjustable platform and use a protractor to set it at a specific angle, 90 degree, 60 degree, 45 degree, and 30 degree. From a constant height of 3 feet, we release a single drop of blood onto the paper at each angle. We label each stain clearly with the angle used. We also mark the direction the blood traveled and measure the width and length of the stain. We calculate the angle of origin using the formula. The width of the stain is 1.5 cm and the length is also 1.5 cm, giving a ratio of 1.0. Therefore, the angle of impact is 90 degrees. Next, we measure the stain at 60 degrees. The width is 1.5 cm and the length is 1.3 cm. The ratio is 0.69, so that the angle of the impact is 60 degrees. Next, we measure the stain at 45 degrees. The width is 1.0 cm and the length is 1.5 cm. The ratio is 0.667, so the angle of the impact is 45 degrees. Next, we measure the stain at 30 degrees. The width is 8 cm and the length is 1.7 cm. The ratio is 0.528, so the angle of the impact is 30 degrees. Now we will learn how to determine where the bloodshed occurred using stringing and trigonometry. The area of convergence is the spot on the surface where the paths of the blood strains meet. The point where all these lines cross is our area of convergence. Before we go 3D, we need to calculate the angle for each drop. We measured the width and the length of each stain. We calculate the angle using the formula. Angle, arcin, width, and length. The area of origin is the specific point in space where the blood source was positioned. Stringing method. Number 1. Tape a string to the head of the blood stain. Number 2. Use a protractor to lift the string into the air at the exact angle of impact we calculated. Number 3. Run the string back towards the area of convergence. Number 4. Repeat this for all strains. Area of convergence is 2D. It finds the spot on the floor. Area of origin is 3D. It finds the exact point in the space where the victim was.